yesterday we did we started co-classes, definition of co-operator. So problem L, co-problem is simply the complement, and collection of these will give you the co-complexity class. So NP becomes co-NP. And we defined this problem called tautology, which is collection of those. So taut is the collection of DNF formulas that are true. Okay, so true means that every assignment is a satisfying assignment. So it's kind of, you can already see that it's the opposite of SAT in a way. And formally we showed that taut is co-NP complete, tautology is co-NP complete problem. And these are open questions, NP not equal to co-NP, this is not known. And equivalently whether taut is in NP or SAT is in co-NP. Okay, so we saw that if we can show NP different from co-NP, then it will imply P different from NP. Okay, so this is clearly a very important problem, as important as it gets in this course. So next is NEXP. Okay, so this goes even above exponential time. This is non-deterministic exponential time, which is a lot of time. It's an NDTM that in every step is making choices, and exponentially many choices are possible. So it's the non-deterministic version of EXP. Okay, so next is union of n time 2 raised to n raised to c. So this is non-deterministic Turing machines running for 2 raised to n raised to c time and every possible c. We collect all these problems, okay, and we call it NEXP, which is short form for non-deterministic exponential time. So it's clear that easy to see that P is in NP, NP is in EXP, and EXP is in NEXP. Right, that's obvious from the definition, because time is always in n time in the same function, right? And NP is in X because of exhaustive search for certificates. But more interestingly, what we will show is that these two questions are related. So this question, that these are different, and this question, that these are different, these two questions are actually related in a nice way. So let's do that. So P equal to NP implies that EXP is NEXP. Okay, so this is an interesting connection. It is telling you that if non-determinism doesn't help at the polynomial time level, then it cannot help at the exponential time level. Notice that the theorem doesn't say anything about the converse. Converse we don't know. So it's possible that in exponential time non-determinism doesn't help, but when the time is less than exponential, then it helps. Okay, so theoretically that's a possibility, although we don't believe it. And the idea here is quite important. So the idea of the proof is to pad a language. Okay, so the idea is that of padding a language with let's say zeros. That's the simple idea. So basically, if you take a So suppose we assume that P is equal to NP. And L is in NEXP. We want to show that L is actually in EXP. So how do you use the algorithm, let's say for SAT, to solve L, this problem L? So the way you can do it is you pad the language with a lot of zeros, exponentially many zeros. So let M be a 2 raised to n raised to c time NDTM accepting L. Suppose L is solved by M, right? Solved in this sense, exponentially many choice making non-deterministic Turing machine. So consider the padded version of L that is related to the idea, actually this L prime definition. Okay, L prime is X padded with zeros for the yes strings. So take all these yes strings and pad them with enough zeros. So that seems silly. Why should this help? So the reason why this will help is that now the input length, instead of being n, it's actually exponentially more. Okay, now the length is 2 raised to n raised to c, and so now actually instead of L being in NEXP, now L prime is in NP. This is what you immediately deduce. So you deduce that L prime is in NP. Why? Because any x prime string in L prime can be accepted, or is in fact accepted by M in poly x prime time. Okay, so this NDTM M which was given to you, which we started with, this actually as a function of x prime, because x prime has blown up significantly to 2 raised to n raised to c, it's actually being solved in linear time in that. Okay, so then trivially L prime is in NP. In fact, I can just say big O instead of poly. Even that is true. It is being solved in linear time. So L prime is trivially in NP, and which means that L prime is in P, because we have assumed P equal to NP. So say L prime is in D time n raised to D. Okay, suppose, so it's in polynomial time, so say the time complexity is given by some constant D, so n to the D time. So now for an x, we can decide x in L in time big O of x plus 2 raised to x raised to c, which is this x prime in L prime, that's the size of L x prime, and in that d, that thing raised to d, right? That's the time complexity, which is upper bounded by, clearly by exponential in x. Let me just say, yeah, that this is, well, this is just single exponential in size of x. So, this means that L is in x. And L was any language in NEXP, so you have shown that NEXP is exp. Okay, so this is how you will use SAT solver to solve NEXP. And this was a surprisingly simple proof. Not much happened here. This is the idea of padding. What about the converse? So if you assume NEXP to be exp, then what does it say about SAT? Are there SAT solvers or not? Okay, what is an upper bound on NEXP? How hard are problems, or I mean, what is the brute force algorithm to solve NEXP problems? So that goes higher than, one level higher than exp, right? Or exponential level higher than exp. So we can define a complexity class doubly exponential time. So E exp. Okay, so E exp is union of d time 2 raised to 2 raised to n raised to c. Right, so instead of 2 raised to n raised to c, you raise that whole thing above 2. So that's doubly exponential time. And again, it's easy to see that exp is in NEXP and this is in EXP. EX because it was and NEXP means that there is an NDTM which is making exponentially many choices. So if you go over all possible choices, then non-determinism can be eliminated, but the cost is the time complexity becomes 2 raised to exponential. So that's 2 raised to 2 raised to n raised to c, right? And both these will be open questions. We don't know whether exp is same as NEXP, and we don't know whether NEXP is the same as or smaller than EXP. Right, just like we don't know whether NP and EXP are different. And similarly, we can NDTM versus TM gives many complexity classes. Okay, just like you went from NP to NEXP, you can keep doing this. You can now define NE exp and so on. And so you can already build infinitely many complexity classes. And alternately we will know that the classes are different, and alternately we will have an open question yet to be solved. So we'll see which ones we can prove. So for example, we can show that P is different from exp and exp is different from exp. Okay, we'll start a topic today called hierarchy theorems. There we'll prove such results. But before that, let me give an example of a good NP problem. which you can call Godel's computation question. So this problem is theorems. So what is the language called theorems? This is the collection of those math statements, well formulated math statements, phi, that have a proof of length n. Okay, provable math statements, hence theorems. So phi is a math statement. So it's well formed by the rules of mathematics or the notation of math. So phi is a math statement with a proof of length at most n. Okay, so these are not, phi is not false and phi is not unprovable, right? And the length is given here. So collection of these theorems, where does it live, right? Which complexity class? Since proof verification is easy, we get the result that theorems is in NP. Right, so the set of mathematical theorems with their proof length, this is an NP problem, because if there is a proof given to you, then you can immediately check it. Right, that is what is part of the mathematician's work. But this gives you an interesting connection that between math and this NP completeness area, that if P is equal to NP, then what happens is every math statement can be easily resolved. Right, why is that? Because you come up with some conjecture, well-formed conjecture, and you come up with a length of the proof. Say the proof takes 100 pages, right? So you give your phi comma 1 to the 100 pages to this SAT solver. Say you have a SAT solver, P is equal to NP, and then that solver will tell you whether there is a proof or not of length 100 pages, right? If 100 pages is not enough, you can try for 200 pages and so on. So a reasonable length proof, whether it exists or not, can be easily checked. So this will essentially mean that there is no need for mathematicians. Right, this is kind of automation of what mathematicians do, which is resolve math statements. Well-formed math statements, mathematicians study whether and try to show whether it's false by giving a counterexample or whether it's true by giving a proof. And that will become an automated process. Yeah, so you can think of this as the halting problem uncomputability that we discussed before. So there the time was infinite versus finite, and here it is within finite we are trying to study that, okay, how fast or slow can you find a proof. Okay, so n length proof, can you find it in poly n time? Exponential is trivial. It just follows from what we had observed here, right? NP is in NEXP. So theorems is trivially in X because you can try out all possible proofs of length n. So that is not the issue, but then, I mean, this computability is not the issue here, complexity is. Right? So that is another reason why PNP question is philosophically very interesting. Okay. Next thing we will do, as promised, these are the hierarchy theorems. Which is separating complexity classes as much as we can. So the results you will see here, they will be of the type that when we fix a resource, let's say time, we will show that if more time is given, we can solve more problems. Okay, and same thing with space, same thing with non-determinism. So within a resource, comparison can be made, hierarchy is there. When the resource changes, then between two resources we can't compare. I mean, we can't, so those becomes open questions. But for a fixed resource, we will solve all those questions now. So we now see that given strictly more, given a strictly more resource, so example, if you are given more time, more space, more non-determinism, Turing machine can solve strictly more problems. Okay, so the key thing here is that one resource is being fixed. We are comparing one resource with itself. So more time or more space or more non-determinism, and then you can solve more problems. P and P is not that question. So in P, you are actually comparing time with non-determinism, and then we have no clue what to do. So how do these proofs run? So the idea in these proofs is, as mentioned in the beginning of in the initial weeks, this diagonalization argument. Okay, we'll use the amazing method of diagonalization to show hierarchy theorems. So use the trick of diagonalization to construct this extra problem. Okay, so this was done in several works, I think, or maybe it was one work with several authors. So this is, the authors of this idea are Hartmanis, Stearns, Louis in the 60s. Okay, so this what the way you show halting problem is uncomputable, or the way you show the basic property that real numbers are uncountable, they are different from natural numbers or even rational numbers. That same idea actually carries forward to computing and in fact complexity theory to prove these hierarchy theorems. So the first thing that we will show is about time. So theorem 1 is that if you have more time, by more I will mean if Gn is strictly larger than f of n log of f of n, okay, which seems like a weird condition. It's not just that Gn is more than Fn, but it's that Gn is strictly more than Fn times log. Then d time of Fn is strictly smaller than d time Gn. Okay, so Gn is this more time, you can solve more problems. That's an amazing result. So let's see how you prove such things. So as I said, the idea is to find an actually design an extra problem. Okay, a problem which is in d time g, but not in d time f. So what is this problem? So let's design a Turing machine in the right hand side. Okay, a Turing machine which is, or a problem, I mean equivalently a problem in right hand side that is different from each one in the left hand side. So we basically have to implement this diagonalization idea. For that, what we will do is we will let our Turing machine run for, I mean we will take a Turing machine in the input. Okay, so and then our universal Turing machine will simulate it for a while for Gn steps, and whatever answer it gets after the simulation in Gn steps, it will negate it. Okay, this is also what we did when we worked with halting problems. So take a Turing machine, run it for a while. In this case, we are truncating this up to Gn time, and then whatever answer comes out of the simulation, you negate it, and that becomes your output. Okay, and we just have to now do the calculation, actual proof calculation to verify what I said. See that it works. So consider Turing machine D, which on input x does the following. So if x is not a Turing machine description, well, if x is not describing a Turing machine, it's a don't care string. We just output no, then output 0. Else simulate the Turing machine that X is describing, right? That M sub X, that is M sub X. Simulate it on itself. So simulate the Turing machine X on X. But the difference from halting problem proof is that this computation has to be truncated, because you want your Turing machine to be on the RHS, right? So RHS cannot take more than GN steps or order GN steps. So we have to truncate at that. So GX steps, which is GN steps. So simulate it for those many steps. So either already Turing machine has decided something or not yet. So if it has decided, or if it doesn't halt, then output 0. This is again kind of don't care answer. I mean, there was no answer, so you cannot do anything, you just output 0. So most interesting comes in the last, which is there was an answer of the simulation and you negate that. So else output 1 minus mx x. So whatever was the answer obtained, you negate it, meaning 0 becomes 1, 1 becomes 0. Right. So now it's clear that this is a Turing machine which is on the RHS, and we have to see what happens with LHS. So D decides a language L in D time GN. Right, because it has only G of n many steps. So, and let's say the language it is deciding is L. Definition, this is the definition of L. So L is in RHS, and the question becomes, is L in left hand side? Right, so is L in D time Fn? So suppose yes, just for the sake of contradiction. So then it means that there is a Turing machine which takes only Fn time and solves L. And you can already see how the contradiction will come, because in step 2.2, in G of n steps, it is answering the opposite, and Fn is less than Gn. Right. So that is where the contradiction will come, because 2.2 is negating that answer, whatever was supposed to come. So let's do this formally. Doing it formally will take slightly more effort. So let M be the Tm deciding L in time C times f of n for all n greater than equal to constant n0. Right, this comes from the definition of d time fn. It's big O of fn times, so it's actually C constant times fn after n has crossed a constant n0. So C and n0 are constants. And yes, so we will now pick a large string describing M. So M is the Turing machine, right, which you are claiming runs very fast and solves L. So we will actually pick a descriptor of Y, and we'll get the contradiction out of that.